I'm going to talk to you about some of the topics that we've been researching, specifically on things that relate to um, energy usage and sustainability around buildings and schools, looking at some stuff that has to do with water heating, efficient water heating, and I'm going to try to relate some of this also to the international context. And then I'll talk to electric mobility fairly quickly. So the first thing that I want to say is just in terms of context. I've done a Scopus search for publications with authors that are from each region of the world. That's done research on transport. And I think it's very important to just contextualize here the sum total of all the researchers from Africa and all the researchers from South America. That number is less than the number of researchers from France that have published on transport. And that's a bit of an eye-opening if you look at the list of countries from which these researchers would come. The first bit of research that I want to show you is this about schools. So similar to South Africa, I know Brazil also has a bit of an equality problem, and the whole of South America does. But a lot of the work that we've done is to assess the energy usage in schools, and we've tried to look at how the affluent schools and the poorer schools are different. And on the slide here, as you can see on the left-hand side, is the more affluent schools, the schools in richer areas. And on the right-hand side is the schools in poorer areas. And these pictures are all according to scale. And you can see there's 1,400 and 1,600, 1,200 children in the poorer schools with that small area. And on the left-hand side is the more affluent schools with only approximately 600 and 700 learners. So it's a big difference, big divide. And these schools are all within 5 kilometers of one another here in Stellenbosch. So this is a legacy of apartheid. And what we try to do is to try to analyze how these things use energy. So how do the energy profiles look different for these schools? And what I'm showing on the screen here is on the top, you can see the affluent schools. That's the shaded area there. The median hourly usage is the solid line, and the shaded area is the range. And at the bottom is the poorer or the lower income schools. And you can see there's a yawning gap between these schools. The inequality is of such a severe state that the poorer schools just use substantially less than the affluent schools. On the right-hand side, just plotting the distribution of energy in the South African schools and comparing it to international schools. And you should be able to see that in all the other countries, even you can see we've got some Southern Hemisphere countries there, Argentina, for example, substantially more. And this is not because our schools are energy efficient. It's because they're left behind. It's because there's no investment in things like computer labs and investment into learning. And air conditioning, climate control, which is another topic that we're working on. So one of the things that we've done is to identify, even though these schools use a little energy, not a lot of energy, to identify where the energy does go. And the majority of energy actually goes into lighting. So as one of the campaigns that we've run, we've replaced the lighting at these schools. And the impact has been substantial. So you can see the bill in one school case has reduced by 37% just by going from more expensive, or at least less energy efficient lights to more energy efficient LED lights. And the problem is these poor schools can't afford to make that investment, but also in many cases, they're just not aware of what they're doing, and policy hasn't caught up with energy efficiency. So at some of the schools that we replaced LED lights or put in LED lights, the government came back and put back the energy inefficient lights when they replaced lights, because that's just part of their policy. So just moving on, water heating. This is something that's also universal, and more importantly so in countries that are coal heavy, like Jana said. And what we've been doing and looking at is to manage electric water heaters. In South Africa, almost all water heating is done with electricity. And given our dire state of electricity, that's a bit of a stupid idea. So in South Africa, another weird thing is our water heaters are mounted horizontally, not vertically, as they are in most developed countries. Because of that, modeling these things thermally and electrically is very difficult. So we were the first people to actually model how these things look inside when the water disperses and stratifies. And the objective of a lot of what we've done is to understand the benefits of doing energy management of these water heaters, because they contribute almost 30% to household load, and also to try to ensure that we don't have Legionella growth inside the water heaters, because the cooler the water is, the more the growth is. And then finally also ensured that the load on Eskom is reduced by doing demand management. And all of this we've done with emulating users, simulating geysers, and running a lot of synthetic data that we generated based on probabilistic models, based on measurements. So a lot of this is data-based. Finally, on the water heaters, what we've also been busy with recently is to understand what goes on inside the geyser, the water heater, measuring the different levels inside the water heater and to understand exactly how much energy stratifies to the top, how much energy at the bottom, and how it disperses within the water heater, running models. Then we get to electric mobility. So I know Brazil and many developing countries have the same. We have what we call minibus taxis. They're called chapas in Mozambique, Njagajayas in Senegal, and then I see the names that they're given in Brazil are quite interesting. Clandestino, Pirata, which both sound quite bad, Fantasma and Puereros, and Combistas. But this is a phenomenon that's all over the developed or developing countries, and it's something that's not really researched well. And what we've been doing is to understand their mobility patterns and to try to prepare for the eventual onslaught of electrifying these vehicles, because it's going to happen and they're going to have a devastating impact on the grid. So the work that we do is split up into analyzing the vehicles. So what vehicles would be required to replace those when it electrifies, understanding the operations. So that's basically 2 blocks there, just understanding how this informal and unscheduled system is going to work when it's dependent on electricity. And then finally, also understanding what the grid impact is and the infrastructure requirements are of these vehicles. So that's just an overview. This slide, I'm not going to go into much detail, just to say the choice of vehicle, the choice of charger, the requirements in terms of distance, range of the day, and all of that are extremely intertwined. So suddenly with electrification of vehicles, it's not just about the vehicle, just about the fueling station. It's about all these things coming together, and it's about electric mobility as a system. And especially in developing countries that have grid constraints, such as Jana just described, we need to evaluate this very carefully as a system and understand that we can deliver mobility, because these vehicles deliver mobility to more than 70% of people in sub-Saharan Africa. It is the mode of transport in sub-Saharan Africa. So we used some of these mobility models that we've generated, and also electrokinetic models that we developed and validated. I'll tell you more about that in a second here in South Africa. We use them to understand how much energy is needed for the vehicles, but also to what extent we can offset that with PV while they're stationary, because they have a morning peak, they have an evening peak, and in the middle of the day, in the middle of the night, they're completely stationary. Just an important point here, a lot of transport and traffic engineers typically use passenger-based data to track vehicles. But if you do that, you tend to miss data. So I know in Brazil, for example, it's legislation that each vehicle has to have a tracker. If you use tracker data, you get a very nice profile that you can use for proper modeling of electric demand. But if you use passenger-based data, that whole secondary peak goes away because the passengers went home early. And that's typically the public data that you can find. Another important thing is when you do electric mobility modeling, you can't use low frequency sampling. You can't do origin destination based sampling. You have to use high frequency sampling, because otherwise you miss the majority of acceleration and the majority of force that's needed to propel and to move the vehicle forward. Some of the challenges that we faced is in a developing context, the maps don't represent where the vehicles go. And that's firstly because the maps are outdated, but also because the vehicles, especially these informal vehicles, they go where there aren't roads. So they will drive in between houses and in between shacks in the favela type scenarios. We also understood after a very short period that the simulation models from Europe and from America don't work in a developed context. The vehicles just don't stop as often. They don't accelerate at the same rate. They don't drive at the same rate. Just as a very stupid example, we found that the minibus taxis only stopped at 29% of the stop signs. They just drifted through, which has severe energy consequences in addition to the safety consequences. So what we had to do is take all the models from America, from Europe, all the simulation models, and try to align them to the driving style here, the road system here, and the vehicles here. And finally ended up that all the vehicles that we simulated on all the different simulators after adjustment gave the same result. But that took some doing. It took almost a year and a half to get to that point. Very important, the stuff that Jana talked about, the grid impact. We have two peaks in South Africa on the grid, and most countries do, a morning peak and an evening peak. And what is of severe concern is that these informal vehicles, when they get to the charging stations in the morning, that'll perfectly coincide with the grid peak that we have because of water heaters heating up. And in the evening, when they come back, they charge up. That'll perfectly coincide with our evening grid, which means we desperately need some form of legislation or some form of control to ensure that all these vehicles don't charge at the same time, because we have 250,000 of them just in South Africa. Importantly, what we also did, we looked at to what extent we can offset that impact by adding stationary battery banks, battery energy storages at the taxi bus stations, and also looked at to what extent we can offset that with solar power. And just a 60 kilowatt hour battery per vehicle reduced the energy demand by almost 50% and the peak load by 70%. Which are substantial. That's a battery and solar panels. In addition, I don't know if it's the same in other developing countries, but these minibus taxis don't only serve the urban society, they also do long distance trips over weekends and holidays, where they basically double up as coaches doing long distance trips, what you'd find in Europe. And a big problem with electric mobility is they will not be able to service that because they cover 2,400 kilometers in a single weekend. And there's no way you're going to do that with an electric vehicle. So we've been proposing solutions for that. One solution is a hydrogen trailer, a hydrogen power trailer, fuel cell trailer. The other option is a battery bank that you pull and then swap them out on the way to the long distance journeys. So this is also some of the contextual African stuff that we've been doing. We've also been importing, or we've been busy importing this for more than a year now. This is an electric taxi coming from China, but because we're in the back of the queue, it's not arrived yet. This should be here hopefully in the next month. I don't know. But what we've also been doing is to retrofit an existing taxi. So we took a 2009 year model Toyota Hi-Ace. We stripped out the combustion engine and the fuel tank, and we added a battery and an electric motor. And this is the electric taxi that is now driving, and it should be roadworthy as well in a week or two's time. And the idea is that with this, we build the skill set, we raise the awareness, and we work towards having electric vehicles in the country. Because one big issue is we have 500,000 jobs depending on local production of electric vehicles, of vehicles. And those jobs are going to die because Europe is going to stop importing our vehicles soon because of the drive towards electric mobility. So this is what we're busy with. Another thing that we've been working that's to do with sustainability. The previous one also obviously very much speaks to circular economy, reusing the components. We've also been building a standalone charger, and this is basically just one big inverter with batteries and a small vehicle that we use to charge. And this is meant for agricultural applications where these devices are probably going to be off grid, and you're going to have to charge electric vehicles on farms without the supply of an Eskom. And finally, we're just doing some grid impact assessments and working towards vehicle to grid applications, especially looking at the taxis, which have substantially big batteries, and also buses to that end.